Hi, this is Chuck Benedict, mentor for Team 997 Spartan Robotics in Corvallis, Oregon. I guess before I start, I wanted to give a shout out to my beloved Texas A&M Aggies. I got my coffee here. The ladies soccer team played South Carolina yesterday, and they lost a 2-1 decision. So they're knocked out of the first round of the SEC championship, which is unfortunate because they've just had an amazing season. But ladies, you will make it to the NCAA tournament. That much I'm sure of. So, Giga Maggies. So I thought I would talk through some of the performance tuning that I've done to the vision processing application that I've been going through in these series of videos. Last video, I talked about some of the performance timings that I was seeing, the differences between running the application on Windows versus running it on the Raspberry Pi. And I gave some ideas in that video of things that I might try. In this video, I'm going to go through those ideas and show that I was actually able to get pretty close to my performance targets by doing some of those and then doing some other things. So let's go ahead and get to it. First thing I wanted to show you, this is the main.java file, and I got some feedback about blowing up the code, so hopefully it's bigger now, and those of you that are having trouble seeing it can read it better. This is the main.java file, and oh, by the way, this is version 005 if you're following along from GitHub. There's also a branch that I put out there called Performance Tuning. But I'm going to move that over and tag it with version 005. So in the main.java file, the while loop, which is doing the image processing, I've continued to decompose the problem to make the application more testable, which is one reason why it looks a lot different. But if you'll recall from my last video, one of the things that I was going to try was to break apart the red ball processing and the blue ball processing into separate components such that I could submit those off to separate threads and have them image processed simultaneously, because in the prior versions of the project I was doing them serially, and because the Raspberry Pi it's a quad core processor, so it has the ability to run multiple things simultaneously. And certainly on my Windows workstation, which this is not a powerful machine, but I think it's got a quad core built into it as well. There's a couple of ways to go about doing it. I'm actually fairly new to Java, so I don't necessarily know all the techniques. I'm actually a C# developer, and C# has a very robust async processing model. But I was reading for Java's concurrency model uses something called futures. So that's what I've done here. If you look at this line of code here, I have my red ball image processor class, which we'll take a look at here in a minute. It has a process method on it for which I feed in the input image to process. And what I get back is this thing called a future. And that's a future of type question mark, which is Java's way, or at least the concurrency model's way of signifying that I'm going to get back a null. I don't basically care what I get back from the process, but when it returns, I'm going to get back a null. And so what happens when this line of code is called is that it immediately returns, as opposed to waiting for process to finish. I get an immediate return, and I get this future variable back, and this variable allows me to test for completion of this process function at some point in the future later. And then it allows me to get the value that's returned. In this case, the value is going to be null. So these three lines of code are returning futures, and so what's going to happen when this loop is run is that these three are going to execute bang, bang, bang. And then I'm going to be sitting down here in this try statement. This get function right here actually waits on this thread that's running. This thread will block pending a result from this red ball image processing future. And then same thing with this next call. This will block as well. Presumably these things will probably finish at about the same time. So then processing will then continue, which will then allow me to call the annotate functions, passing the input image in, and the annotate functions are where I'm drawing. If you'll recall in my prior videos, I draw a circle and I write the color label of the balls. These are the image processing that's going on is looking for racket balls, and it's drawing a yellow circle when it finds a ball, and it writes the color of the ball inside the circle. So that's what these annotate functions do. And then finally, I put the frame to my image source, which we'll take a look at here in a second, of the resulting image. You'll notice that I made a function call here, and I extracted the pumping of the images from the image source. This was not, the fetching of the images were happening in line with the processing of the images in my prior versions of my project. But in my last video, what I noticed is that there is some time taken for I/O of getting the images off of the camera. So I figured, aside from processing the images concurrently, why don't we also call the I/O concurrently, so that I can use 3 of my 4 cores to do something useful simultaneously, and thus speed up the whole process. So you'll see down here that I also then take my image future, which I obtained up here, and I call get on it to block, presumably to wait to get the image back as well. Of course, by the time I get down here, I'm sure I have the next image already, and so it basically throws the resulting image in my input image variable for the next trip around this loop. So that's how futures work. They're pretty simple. You'll notice that there are some nasty looking try-catch blocks you have to put around the getting of the future. One thing is that you have to implement an interrupted exception, because this get can be interrupted. The thread can be interrupted, so you have to do something if that interrupt occurs. And what I'm doing is basically passing the interrupt back up the call chain, because you don't want to swallow the interrupts here. That can cause all sorts of weird problems. And then if I get an execution, so the execution of this get, remember, is waiting for this function to finish, and that function itself can throw an exception. So if it does, that exception can get caught here, and all I'm doing is just simply printing out the message and continuing. You know, thinking about it, if this input image is not gotten for some reason because of an exception being thrown, probably I need to clear out the image. I need to set it to blank, so that when I go through this again, the image will be empty. But anyway, I haven't done that here, and I haven't tested what's going to happen here, so that's probably room for improvement. So let's take a look at some of these functions, because while you can see the asynchronous mechanism working here, how it actually works is important to understand. So let's go look at the image processor. So the image processor class, I've decomposed from my prior projects into a bit finer granularity, and in particular, the constructor for this class takes 2 variables. It takes an image, it takes an interface to an image pipeline, and it takes an interface to a network table writer. And we'll talk about that here in a bit. The process function that we were just looking at, the call to it in the main Java file, does a fairly simple thing. It returns the result of an executor submit function, and the executor is defined up here at the top in this static variable of executors, and this is from the Java concurrency library, of creating a new single thread executor. And think of a executor as a pool of threads that are available waiting for work to be done. And the way that you call on that pool to do work is by using this submit function. And I only have 1 thread being created in the pool, which is fine because I only typically have 1 instantiation of the image processor for which I'm going to simultaneously do work. Now, in reality, I have 2 instantiations, but on any given instantiation, I'm only going to have 1 call to the process function going on at any given time. Inside the submit function, then, I have a inline method being created that simply calls the process method of my pipeline, feeding the image that I get from here. And then I call my network table variable that got passed in this constructor, and I call the write method, which writes to network tables. Same as before, but now it's been decomposed and stuck into its own function. And then I mentioned before there's an annotate function which draws the circles and it writes the text into the circles. So the future, the act of calling submit returns, this return will actually return a new future, and the result of the submit returns null here. As I'd mentioned before, this question mark means return type of null once the function finishes. So a couple of more decomposing things that I've done. I've created this interface called eyeball pipeline, which genericizes the 2 different pipelines. I've got a red ball pipeline and a blue ball pipeline, but I've created an interface which only has these 3 functions in it because this is really all I care about. I obviously want to be able to process the pipeline. I want to be able to find the blobs that result, and then I want to get the color that I care about because that color, that's the label that gets printed out on the circles that are identifying the balls on the resulting image. And then I have actual implementations of that interface. So I have my blue ball pipeline here that implements eyeball pipeline, and in particular, once this variable is created, I create my own pipeline of type blue ball grip pipeline. So this is the actual pipeline that gets created from grip. And this, by doing it this way, this allows me to add some additional functionality to this implemented pipeline that the grip pipeline does not have, and it allows me to kind of keep this by itself so that when I regen the pipeline through grip, I don't have to make any mods to it. But as you can see, this is where I add the color for the drawing of the circles. Decomposing the problem also allows me to better test, and I'll be in future videos showing how I can go about testing these things using JUnit, I think it's called JUnit, and Mockito, which makes this testable without having to actually run the project. So it makes that really helpful. So given all of that work, as you may recall if you watched the last video, I was trying to get somewhere around an 8x performance improvement. And with these improvements, I was expecting at least a doubling of the performance because now I'm doing work simultaneously, whereas before it was done serially. So I'm looking at about 100% improvement or so from this. And so why don't we go ahead and run the application on the Raspberry Pi. And I have some balls over here on the floor. I'm going to go ahead and pull up a browser to look at the result. And I have talking to you on one camera, and I have this Microsoft HD 5000 Life Cam that I'm going to use to point at the balls. And I already have this running, so let's go bring up my browser. Now, one thing you'll notice from prior videos is that the video size is smaller, so that's how I have gotten quite a bit of performance gain because I really didn't need it running as big as I had it. I think I had it running 640 by 480 before, and so now I've cut the size in half on both axes, so I'm getting a 4x improvement on speed. And as you can see, when I move the camera around, I'm getting very good performance. I'm estimating 25 frames a second or so, or perhaps a little better. Now my detection is not working so well because I have a white balance and a brightness issue when I switch back and forth between the Raspberry Pi and my Windows machine, which I'm going to correct later. But as you can see, the detection is working reasonably well. Blue ball detection again is having problems, I think, because of the white balance. But as compared to prior videos, you can see that the tracking is much superior, and that is from the two performance improvements that I've made. Running it multi-threaded, running the ball detection multi-threaded, and reducing the frame size from 640 by 480 to 320 by 240. That effectively reduces the size of the frames that the Pi has to produce by a factor of 4. So I've got a factor of 4 improvement, factor of 2 improvement with the it multi-threaded. So thus now I'm getting to my 8x performance improvement, which is kind of what I was targeting. So the net of this for me suggests that the Raspberry Pi is capable of decent performance on vision processing. You do have to be careful with how you construct the grip pipeline. You can't do anything more than really is absolutely necessary, but you can run a couple of pipelines concurrently. And as long as you keep your image size down to a manageable level, it seems to work just fine without having to run an optimized build of OpenCV, which I may yet do to see what additionally I can get out of it. But for most people, you don't want to have to go through that hassle. And if you can get what you need with the way it is, then why bother? So hopefully you've enjoyed the video. Thanks for watching, and good luck with the upcoming season.